Welcome, everybody. Welcome here at IEP. Welcome, everybody that is attending this seminar session online. My name is Stefan Ploegman, and I will give you a short introduction of what we are going to do this afternoon. It's going to be a seminar and demonstration about what we call real-world electrochemical impedance spectroscopy testing. Using high power multi-cell measurement. I will start with a short introduction, will not take too long. After that, I hand over the microphone to Modesto de Moraes and Esau Cardoso, and they will explain about IEP, what the activities are, and about the new high voltage testing lab that they are building. After that, we go to the main topic. My colleague Jürgen Süterlütti will take a deep dive into what we mean by real-world electrochemical impedance spectroscopy testing. This session will take about an hour. And then also for the people online, we will stop the session. There will be a short coffee break here. And then for the people who are interested, we can go to the new high-power facility, which is a short 5-minute drive from here by car. If you don't have a car, we can maybe do some carpooling and everything, but we can arrange that after the session. And there we will do a live demonstration with a second life battery that we have here, so you can see the system in action. And then there is some discussion time. So we will probably be finished then around 4:30. We'll see, and then everybody is free to go. So it's a free seminar, but nothing comes for free. So you just have to listen to me for a few more minutes about what Gantner Instruments is doing. We are a company specialized in precision measurement. We are based in Austria. Very nice for skiing, hiking in the mountains. Would recommend to visit it. We've been around for 40 years already, specializing in analog to digital conversion. And over those 40 years, we've grown out into one of the market leaders into in data acquisition technology. So I also want to give some credit to our Portuguese partner who has been helping us to organize this seminar. That's the company PerfectDecibel, where we have Carlos Gomes here represented. He is also the representative of Gantner Instruments here in Portugal. So for any follow-up questions after this session, please feel free to contact Carlos. A few more things what we do at Gantner Instruments. We specialize in precision measurement. On one hand, we do this for mechanical power, and on the other hand, we do this for electrical power. So think about things like vibration measurement, strain measurement, temperature measurement, but also high voltage measurement, power analysis, various type of measurements. We actually do this for different sectors. So it's not only involving batteries or renewable energy, or we even install our precision measurement equipment on bridges. Probably most of the bridges here in Portugal, at least the critical ones, if you drive over it, pretty sure there is Gantner Instruments technology on the bridge for structural health monitoring purposes. So it's a very diverse. But originally, Gantner Instruments grew big in the automotive industry with data acquisition systems for engine testing. And already very early in the beginning, the German automotive industry was changing to electric vehicle technology. This was already the year 2008. And we evolved with the German automotive industry into developing data acquisition technology for electrical vehicle testing applications. So some of the applications where you can see our data acquisition technology is, for example, in battery testing. This is the General Motors battery test lab. They do various testing on R&D on new battery technology for electrical vehicles, so charge discharge testing, nail penetration testing, all sorts of things. And with our high voltage data acquisition technology, we are recording all the data and making it available for further analysis. I lost my control. Yes. Just another quick example. TÜV Süd in America. They have a whole facility for thermal runaway testing on batteries, where they just slam a nail into the battery and see how it responds to that. We equip their whole facility with data acquisition, including video. So we are aligning video and the real measurements in terms of temperature and forces and pressures all together in one data acquisition package. And a little bit closer to home for the people that are here at IEP, we work with a company called PRE. They are based here in Trova. They are a manufacturer of battery management systems for electrical vehicles. So they have design and production lines for BMS products that go into cars. And at the end of the production line, there is a Gantner Instruments data acquisition system doing the end-of-line production testing of their BMS product. Now, the question is, how do you go from automotive to electrochemical impedance spectroscopy? As I said, we were already in the very early stages involved with electrical drivetrain testing, battery testing. So over the years, our product range has evolved from basic data acquisition to high power analysis, to standby current measurement. So in a car, you have a lot of control units that control your windows or your windscreen wipers. But if they don't do anything, they are still in standby mode and consuming power. There is a lot of development going on to reduce the standby power that these devices use to make electrical vehicles more efficient. So we work with companies like Audi and Volkswagen to design a product that can measure very accurately the standby currents of the control units. And 2 years ago, we got a question out of the industry if we could do something with qualifying state of charge of batteries using a technology called electrochemical impedance spectroscopy, but not on cell level, but really on battery module, battery pack level. Okay. And so being able to test that with the actual power to the battery and measuring all the individual battery cells in parallel. Wow. So we developed a system for that. And this will be the topic of today's seminar. It's on one hand used for batteries, but in the last year, we've seen a growing interest also from the hydrogen market. There's a lot of development going on in electrolyzer stacks, and the same technology applies to electrolyzer stacks and fuel cells. So that's my short introduction for now. Then I would like to give the microphone to Modesto.
Thank you. All right, no, I have no presentation. Thank you. First of all, I'd like to thank you all for coming here to IEP, to this seminar. And also like to thank all my colleagues that prepared this event with us and with Gantner and PerfectDecibel. My name is Modesto Moraes, as I said before. I'm the manager at IEP for research and development. And also I'm very well inside of the preparation of the laboratory, power laboratory, which you can see at the end of our presentations. Why we are here with about the EIS. In our project, we are working now. There is a concern for us because we are working with the batteries which are not new, so means for second life applications, and we are very well concerned with the safety. Safety is always a concern for us as a test house, essentially electrical safety, and using AES for testing those batteries on use or for future use is important point, because we want to know if those cell packs or batteries are really in good conditions to be operated on the real market, means for instance in households or even in companies. This is a key issue which has to be solved. Is not completely managed as we saw from most of the applications now. And why we choose the Gantner solutions? We saw that from the applications which are in the market, those solutions from them are industrial grade. They work very precisely and with very precise and even with a very accurate way of getting measurements, and actually fast. As you will see later, you can measure many cells at the same time, and every measurement you want to do, you can repeat it very fast and then get the results, which could be useful varying the conditions of testing, like temperatures and pressure and so on. I'd like to introduce my colleague now, Celso Cardoso, which is also here. He's going to present in more detail of the laboratory and the capacity we already have installed there. Thank you very much.
Well, good afternoon, everybody. Thank you for being here. I'm Celso Cardoso. I'm the technical responsible or the responsible for the testing laboratory of IEP, and I will make a short presentation of what we were and still are, and what is the aim of this main project of this building. Okay. Okay. So this is the virtual images of the laboratory. We have you can see later on the new building. This building was the main objective of this building is to enhance all the capabilities that we already had of EMC, electromagnetic compatibility, to newer technologies, namely in mobility and energy. So a brief history. In the past or till now, we have different areas. Electrical equipments are almost grid connected and as standalone with no connections to other parts. Mobility was full based, and electronics makes in their electronics makes only use of the control of the systems on vehicles. And another issue was the environmental concerns about the efficiency and labeling of equipments. Now and in future, all these three parts, if we may say, share the same ecosystem. So batteries, power electronics, renewals, all are converging to the same equipment. They are not different equipments, but all equipment. When we talk about mobility, when we talk about batteries in household appliances, well, all that ecosystem share the same product. So we focused our knowledge to these parts for mobility. Electromagnetic compatibility is not only for grid-connected equipment, but also for mobility systems like car components and so on. And also energy. We are not talking about controlling small energy equipment like it was 99% of the occasions, but now every equipment have high power, and that's the aim of this laboratory. So we try to with this lab to converge and to make possible to respond to all this ecosystem as one. So for this we have this is our new EMC SAC5 chamber for testing not only large equipment, heavy equipment that can goes up to 2 tons, but also small vehicles and in the location of the table, and also for components. As you see in the right part, you have a table. We can there test components, high power components for mobility. This is for the EMC part. Also, the components part, as I said. Also, we have some partners, and we will be able to test small vehicles like e-bikes. And in the right down, there's a reverberant chamber that enables us now and in the future to test immunity of high reliability systems, like in military or in the aeronautics systems. It's coming very soon, and we are already prepared for that. We have circulating systems together. Just we are not trying to just measure perturbances or disturbances for low to high frequency. We can do it in high power environments. So we can simulate everything that goes from photovoltaic systems, battery systems, with circulating systems that can put in real or real world likewise systems of operation. For safety, we try to focus also in the large systems for batteries and electronic systems, vibration and mechanical tests combined, combined temperature and vibration, circulation of energy flow up to 400 kilowatt, battery, automotive, and component systems, as I said. The aim here is not to give full answer to these standards that I mentioned here, the R100, but to be able to test, to perform tests in very specific and difficult conditions. That's our main objective. Of course, the simpler systems, we can also do it. But the aim is to give answer to difficult conditions of testing. So these are our circulation systems from Regatron, which are systems that are very configurable, not only in DC component, but also in AC component. We can put together DC and AC component up to 10 kilohertz, which is a very useful tool to perform tests in different kind of standards, OEM standards, and the like. The system that I was mentioning, the combined vibration and temperature testing, that goes up to 74 kilonewtons, and connected to a chamber that goes from 1975 degrees up to 180 degrees. And as I said before, this is a chamber. Of course, we can, we have several chambers, small chambers that can go from -40 to 120 degrees with the humidity control. But this chamber is 3 meters high and can put a battery pack inside. It is prepared to test battery packs, and also large equipment and very powerful equipment that can be connected to the circulation systems that I mentioned before. Also, this Gantner system that will be said, we understand this is a very open tool as an acquisition system, very precise and very high performance, high frequency acquisition systems that now we are using in EIS systems, but can be modified to any kind of technology that can be that in the future can appear. So in the general overview, we enhanced our capability to mobility, not only the circulating vehicle or all the components, but batteries and energy. And this is the aim of this laboratory, this new installation, this new building that will be able to respond for the difficult part of testing and major demanding test facilities that IEP is focusing now. So in a very last slide, I always like to mention this. I understand that many manufacturers develop their products, and in the end, of course, and in the end, well, we have to certify, we have to see if it is okay. And what we know for experience is that when you do it in the end, things can be difficult to manage, and cost of doing it at the end can be large. So what we try to convince and to work with manufacturers is to integrate in the beginning of the project, when it is on paper, to test it on all along the project, to get a final product that is almost 100% assured that it will pass on the legal requirements that products have to fulfill. So this is our experience, and this is why our not only to analyze it and to evaluate the compliance on the final, but also and most to make part of this development progress of the products of every manufacturer. And that's it. Thank you.
Right. Okay. Hello, everybody. My name is Jürgen Sutterlütti. I'm also with Gantner Instruments for more than 10 years now. And I would like to show you more insights about electrochemical impedance spectroscopy, how you can utilize that, where you see added value on it. But before we start, let's do a little bit of a check of the attendees here. Who of you have already done a real-world ICE measurement? Hands up, please. Okay, so we have already 10 people. Who of you thinks that EIS measurement data is helpful for your work? Less than, okay. So we will see how we can convince you that there is value in the EIS data for your work, whatever the device under test will be. At Gantner Instruments, we have the opportunity to combine a lot of different data acquisition concepts, measurement principles for industrial needs. We are doing a lot of battery, fuel cell, and electrolyzer testing, but for that you also need high power, high voltage devices. So we have the ability that we have really, we can measure high voltage directly to the device under test, but also on the bottom you will see that we can easily do also impedance measurements. When we go to, for example, mobility, the power consumption of ECUs is a topic. And when you have mechanical and electrical components like an e-axle, you also want to understand how the power conversion from electrical and mechanical efficiency is going on. So this is more or less the Gantner world in the spectrum here. Now, doing the seminar today, we really want to focus here on the electrochemical impedance spectroscopy, which builds up on the whole Gantner data acquisition platform. And the good thing is that we really can combine EIS also with time-synchronized time series data acquisition. So we can measure current and voltage at the same time as EIS. Good. One other topic, which will sooner or later come to a lot of people, maybe also in your research or practical career, is that we that you have to integrate hydrogen technologies like electrolyzer fuel cells into the system. There, it's a similar pattern, it's a similar approach that you can measure high voltage directly on the electrolyzer, and also EIS is there helpful to detect and to improve the product itself. We will go now step by step into the principle of EIS, the benefits and so on. But to give you a short heads up on what we are aiming for is that we really want to adopt with the industry needs. A lot of you start in the research, then you have cells where you need to have higher currents, then you need high current systems, what Gantner can supply, what we are applying here at IEP. But then it comes also to multi-channel systems. So you want to measure more at the same time because time is a limiting factor. And then you want to integrate that very easily into your system. So you want to connect with open APIs, with Python and so on, so you can control it together with the climate chamber and so on. So that's why we really have here an open system, which also allows you to do your predictive maintenance and also your advanced analytics tasks. This helps all that you can send the data to your platform or to a cloud where you can then post-process the data. Now, let's start. What is EIS? It's quite simple. EIS is really a diagnostic method. It's non-destructive, and it really can be applied for batteries, fuel cells, and electrolyzers to see how the electrical fluctuation is behaving over time. And with that data, you can check the system health. It guides you also where you can optimize the performance of the device itself. And it helps you to find the inputs for the holy grail about predictive maintenance. Everybody wants to have predictive maintenance and perfectly have the digital twin, but with EIS data, with high quality EIS data, you can optimize your model, qualify it. And nowadays, EIS is changing a little bit the place in the world of research. So far, in the past, the last 15 years, we are working here together with well-known experts in Europe. For example, Material Mates Instruments out of Italy, which did the first high-power EIS system in Europe. At that time, it was still in the lab with limited current, limited amount of channels. And now we are able to combine that know-how with the Gantner data platform to enter the high current multi-channel system, which is then able to apply for really module battery packs and higher power systems. Good. EIS is applying we have always a lot of more interest of people, so that's good. So we'll continue. That's good. So EIS, how is the measurement performed? Well, you apply a sinusoidal voltage and read the current back, or you do it different. You just apply a current and then you read back the voltage. And if you do that on a system which is in a linear state, you can calculate the impedance and you can go along with different frequencies on the IV curve characteristic. Of course, as we have frequency involved, it's a complex number, and this impedance we want to plot over different frequencies. Typically, in our world, we have ranges of interesting frequencies from millihertz up to kilohertz. The system can go beyond the lower end and the higher end. When you have higher frequencies above a few kilohertz, you quite often measure your test setup and your cabling and not your device under test. So that's why you have to really understand where is my device under test information and where is the setup. We'll come to that. Well, why does it matter with EIS? When we have that AC signal on top, we can really superimpose a DC current and bring it to the real world operational point. And that's important that we do EIS not just at an artificial point of operation. We have to do it in real life. So batteries should be charged, discharged, or with state of health of 60%, for example. And there we want to have EIS because then we have direct feedback about the device under these operational conditions. The same applies for temperature and vibration and so on. And as all elements in the electrical energy systems, IEP wants to cover a lot of different electrifying things. EIS is really helpful and relevant for batteries, fuel cells, and electrolyzers because we see that physical chemical processes everywhere in these applications. When you have all that EIS know-how in place, then you have 4 points what you want to achieve. Well, in-depth battery health and insights is a target. Non-invasive analysis is a big benefit. You don't have to open something, you don't have to unscrew something, you just need the right connector and access to the cells or the whole module. You can get really a comprehensive impedance breakdown, so you see quickly what's going on your device, and with that you can do your predictive maintenance, or you can also do cross-application facility, which helps you really that you can compare A versus B, different product benches and product ranges, product batches, that allows you to quickly innovate and quickly give feedback to your production site, for example. Today, EIS becomes very often popular to a lot of people because they suddenly have to change into the high power, high current mode for applications. Batteries are getting bigger because they're cheaper. So that's why energy-related electrochemical studies have to be done much more often. That's why EIS is one of the preferred choice. People want to have faster acceleration testing. People want to have a lot of detailed degradation mechanisms of the cells in a parallel way. That's why really EIS has changed its position in the industry. It's out from the lab. It's now in the applied certification bodies, in applied research for big industry teams, because it shows them the benefit and can accelerate research and product development. So that's why we are here. That's why we are focusing on that. Well, it's a very powerful analysis tool. We have a black box. Let's take a second life battery, which comes to IEP. Then we have a lot of questions. What is it? We know maybe the brand. We know maybe we have a data sheet. Maybe we have a connector. That was happening yesterday in IEP when we did some tests. But then we do a ICE measurement. We get an IQUIS plot out of it in the middle. You see in the different colors what are the typical responsible shapes in an IQUIS plot for the equivalent circuit, like the layer, like the charge transfer, diffusion effects, or the electrolyte. And then you could easily create your equivalent circuit out of it. You are the expert of the device under test. You are the one who can do the equivalent circuit. We are not, just doing the measurement is A, but B means also knowing the metadata, doing the fitting of that thing. So this combined is very powerful. You need a lot of information what your device under test is. The more you know, the better you can understand and compare relative changes over time. So this is more or less the idea of the method itself. But just EIS is not alone. There's a reason why at IEP they have also climate chambers, shakers, because you want to see how the battery is operating at -20 degrees, at 40 degrees, how it's operating at different state of charge. So you have to measure also the different properties of the battery at the same time. For example, it also helps that you put some strain gauges there, because in the battery packs, the prismatic cells, they also expand. So for other applications, that's also quite helpful that you can combine that. And a lot of people report that thermal runaway is visible with EIS measurements much more upfront than you see it visually or with an infrared camera. So all this experience helps you to accelerate your experiments. Okay. It's important that EIS plus time series data gives you really the full system visibility. Just one measurement alone is not everything. You cannot just go with the infrared camera and say, I'm now watching thermal runaway. Try to find it. You also need some current voltage measurements. And if you have EIS on top, you even detect the changes very fast. Okay. So we are now in a situation where we can quickly discuss the different needs for the industry and for guys like you. Because at the end, people want to interpret the EIS in the battery operational context. So this is, you want to understand, I want to have my operational thing of the battery. That's why you want to measure current, voltage, temperature, and strain, and record that over time. So I think that's an important need. Then you also want to compare multiple cells under different conditions and similar measurement conditions. So you need true multi-channel. If you just do that one after the other, the state of charge may change, the temperature may change, so multi-channel is important. And you also want to link impedance changes to the operational point, so that's why you need a lot of synchronized data acquisition. It's not helpful just to say I put the battery into state of charge 60% and then I'm doing an ICE measurement. When you are in the nonlinear area, that drifts away, and then you are wondering why your result of the equivalent circuit is not looking as you expected. And when you have a lot of transients, so fast changing behavior, that's also important that you can check that with EIS. That's why you have to measure not just once per second. We are measuring 100,000 times per second to capture all the transient things. And then we have also modules and packs on the battery side, where you also have, for this you need the high power capabilities, because when you're in second life or first life, you want to do beginning of life testing, check the whole system quickly and get more or less the DNA with the EIS frequency. Okay, so overall, we have our black box in green. We do an ICE measurement in the curve, but we also measure the other parameters, and that allows us to have a very, very accurate equivalent circuit for interpretation, for digital twin modeling, and this is the interface where Gantner delivers you the best-in-class data. That's a system setup. We will have on the live demo later on the option to watch everything live. But overall, in a short thing, we have here our data acquisition cabinet, which is connected to the device under test, which is a battery. Each cell, we are measuring the voltage, and with a shunt or another measurement device like from LEM or from DaniSense with a current transducer, we measure the overall current, which is flowing through all cells. And then we have a power source, which is able to charge or discharge the battery. And on top of that, we modulate an AC signal on it. And then we try to measure that AC signal, which is very, very small. When you, for example, apply 5 amps and 1 amp of AC current, the voltage response is in the range of 1 or 2 millivolt. Now you imagine you have a very big battery pack, let's say 800 volt batteries, and you want to measure 1 millivolt, 1 or 2 millivolt on that. That needs a special data acquisition system, which is still synchronized and has all the safety and galvanic isolation as well. If you do that, you can get curves like that, which are at different temperatures, for example, and soon we will have also this type of charts out from IEP, because they have all the capabilities to run the modules, the battery packs for that for characterization. The same principle, some excursion quickly to the electrolyzer or fuel cell world, we can also apply with the electrolyzer there, and then you also get curves like that. Here is an example about the high power electrolyzer, because their current densities are much higher than at batteries, what is published. But I just want to show you that how in the parallel world you see the differences. So this is a 300 kilowatt PEM stack, which is running on top with 1.5 amp per square centimeters. And then you see only one cell, which is an outlier. That's mainly the manifold. So you see immediately at the position of that cell that the manifold, if you know the whole system, is there. If you now increase current density, you suddenly get two different outliers. Most likely the one is different temperature on the bottom right. The other one is some biphase induced issue, which the people on the electrolyzer world know. So that helps us really to see that when you increase the different power, the energy density, you can really grow out from the kilowatt range to the megawatt class and put that into the field. So it's also possible that you do EIS for full containers on top. Because that really gives you a very good decision also to quickly see what is the status of the device itself. So our systems are here to be applied for things like that. At the end, everybody knows the Swiss Army knife, which is a multi-use tool, and EIS also can do that. So it helps you to really give you full visibility, that you can avoid any misinterpretation, because just one measurement alone, just state of charge, will not give you the truth. You have to combine the things. And when you combine EIS with time series data, then you get really the complete overview of your system. And I think that's quite important, that when you have a second life approach, that you want to inspect the things, you just take the time series measurement plus EIS, and that gives you most likely the fastest feedback what you need. Okay. The system what we will have in the IEP lab is a very modular one, but I will introduce it roughly, and then we will also have a more detailed look on it when we do the real world testing. It starts on the bottom with a power source. That can be different kilowatt classes from 9 kilowatt, 18 kilowatt up to megawatt. We are selecting here Regatron for that, which is able to modulate up to 10 kilohertz. Then you have a lot of an air deflector to make all the thermal management. You can measure also temperatures with thermocouples, for example, and then we come to the EIS DAC modules. So they are really special purpose modules that you can measure this small millivolt signal on a very high potential. Then there is an Ethernet switch, so everything can talk to each other, and the main switch. And of course, there are safety measurements in it. On the right side, we have a EIS engine, which runs on a controller. So that's a real-time Linux system, which stores all the data. And then you can select how many inputs you want, how many different analog or digital inputs you need, and so on. Overall, when you have the system, it's really designed for high power. So the cabinet is already designed for all the requirements on that. We can have here a system which covers all the relevant frequencies from millihertz to 10 kilohertz. Everything is synchronized. It's a real-time system there. And you have also interfaces like EtherCAT, which is quite often used in industry, but there is also Python or CAN interfaces or even LabVIEW, which people are using nowadays to control our system. So when they want to put that into their automation system. At Gantner, it's quite important that we are using open API, so there's no lock-in principle. You can really use everything and have access to the data. And we are also sharing raw data so that you can check if the impedance is really calculated in the right way. Good. A few examples about who is using EIS solutions. It's across the industry. We have a lot of R&D labs. We have also a lot of testing houses there, universities which are doing new tests, even people who are developing battery packs for space, which have -40 Celsius and so on. They also see value of EIS. In the automotive, you know Schaeffler, you know Bosch, and system integrators like Locioni and Crystal and Zeibt, but also universities who are using EIS, not just for batteries, but also for chemical processes, where it gives a lot of help to see the changes there. Quite important is that these people are often starting with small systems, then they upgrade, then they parallelize, and then they also integrate it into their automation. Okay. Now we are starting into some technical details, how the EIS data acquisition works, because that's quite interesting how we do all that data processing. So when we have our battery, we have a DC potential on the left side and a small AC that's much more magnified than in reality. And then you have to find somehow a solution that you can just amplify the AC part of it. And this is what our data acquisition module on the right side is doing for all channels. And with that, you can then have a current and the voltage information and calculate impedance in the real world. How this is done? It's simple. We just measure at the beginning the DC part. feed that back, and then we just compensate for that. And then you have a small millivolt signal which is in your noise. And to find out information in noise, when you have it synchronized, you can apply here the lock-in principle. So you multiply your noise with your target frequency, and then you get the information out of current and voltage. That's quite a very elegant method. It has to be synchronized, and then you can immediately get the magnitude, the phase, or real or imaginary part of the signal. It's 24-bit. It has also additional features in it, like you can filter the data. You can do, there's some other amplification, and it has all the galvanically isolated stuff, because when you are on battery packs on 800 volt and you want to measure it 550 volt your cell, which is 3 volt, you need the right galvanic isolation. Safety is a big concern in all that things, so that's why you have to be able to have a good, safe galvanic isolation. Okay. When you have multiple cells on the left side, we have a battery pack there. Each of them has the input of the data acquisition module. Then we measure that. We get voltage and impedance from each cell. We also measure the current on the bottom. And as everything comes from the same reference generator, it is synchronized, so we can easily calculate then with our EIS engine the result, and then you get your Nyquist plot. You can control the system from the Gantner platform, or you can control it from your Python environment. Okay, we skip the technical details. This is, again, the lock-in principle. If you have here questions, we can discuss later on. But that it's quite important that you have that capability on board to be fast, because you will, when you do the ICE measurement, we cannot wait until it's finished. I mean, sometimes it takes half an hour, and then half an hour to find out, oh, I had the wrong setting, is not good. You need, after each frequency point, we provide the customer with the result, so it's instant. Okay. Now I have here some demos. That's just a preview for everybody who will join us on the lab later on. You will see all that screenshots, and we can go into all the details. We also have cameras able to combine, so you immediately see that the thermal runaway, but we will skip that for this session. This is a data set from yesterday. Today you will see a much more nicer Nyquist plot. So we will do a real world measurement together in the lab there. Okay, we skip the demo. Now a few words about second life batteries, because at the end, IEP wants to push in that direction. I think Portugal has here a strong decision taken. We see that the market will grow exponentially, so you have to prepare at the beginning very well. And a lot of research groups are doing that, especially when you have here national interests of all the raw materials. It's quite important that you're ready, that you can bring the car batteries back to the system, either as second life or at least use the raw material. So the gigawatt hours which will come in 2030 are in the 50 gigawatt hour range, going up to more than 300 in 2035. So that's a lot of capacity. You can use that, especially when you have the things already in your house. Doing that, there are challenges. The main 6 challenges, what literature tells us, and also what we see, and also what IEP is facing, is that you really have batteries where you don't know what was happening is, then you don't know the history. And if you have a black box, you have to somehow start on your own what you get. Battery passport is an answer for that, but that's implemented 2027. So we have to live with no information for the moment. And you don't know what is, when you start in the second life business, the pricing of the batteries in the first life cycle is also changing your demand, your success, and your speed, right? So you have to see that. And then you also have to be able to do quickly diagnosis, and also for that you need open standards. To access the data, the track record of your batteries, how many cycles are there, that should be open. For that, on the Gantner side, we can also integrate CAN data from the BMS if needed, so you can use that in parallel for your interpretation. When you select the batteries, you have to understand what is my target application in the second life. Is it stationary storage? What are the charging rates and so on? So it's quite good that you select and sort it out for your target application. And at the end, if you want to bring that into your house, somebody has to take care about safety and liability. That's the biggest question of the people, but a lot of people are there and say, I'm willing to take some risk. I put the second life battery from cars like Mercedes-Benz, put that into stationary storage, and I have a business opportunity. So when you know what the battery had done in the past, how they were treated, it helps you. And I think with more and more data acquired at IEP, you can also give there some guidance, give there some evidences when you have the feedback loop closed. I think that's quite important that you have here a very good start. And the second thing is you just cannot characterize the battery by electrical tests. You also should check thermal things. You should also check how they react in the mechanical things. So people, when they start, for example, in Norway with the second life business, they have the batteries coming in, they have to be disassembled. They are using robots due to safety for the dismantling, and then it started. So this is a whole new thing, but we have to start with one topic. And when you get, for example, from one automotive OEM, the battery spec, you know how they are processed. You can build up your model with all the data and the testing, and that helps you to make your decisions. At the end, you see in gray here the battery life cycle, but at the end, when they are end of life, we want to give them a second life, so we have to repurpose the things. We have then to remanufacture it and reuse it, so they are going again into the cycle. And once that is finished, once there is no reason to use it for a second or maybe a third life, we try to recycle the things and use the raw material. That's the ecosystem where we are in. And you need a decision tree for things like that. So there has to be criteria, there has to be a decision matrix. What do I next? If the criteria are here. And the most important thing before you start with all that is you should know as much as possible about the device under test you are getting. So collaboration with the original vendor, with the and having data about the history helps a lot to justify what is the second life application. And I tried to summarize a lot of things for second life and how we can use EIS for that. That's a lot of text, but that helps also later for a lookup when you are in situations for discussing that. In the second life, we have the second life battery. And when you have that coming in, we have to test it. Of course, there's a challenge that you want to understand the history. But when you have high power EIS, you can rapidly flag that and understand how the device is behaving. When you have multi-channel, you can do everything in parallel. Modesto was mentioning that you can speed up the things. And the additional measurements you have to do is really safety checks, visual inspection, maybe thermal infrared checks. The same also when you want to do module matching, it also helps that you can cluster with high power EIS the modules quickly. With multi-channel, you can measure them at the same time, see their response at different temperatures, and then you can really judge and estimate the right capacity. Once they are up for recycling, maybe the last line. So some units are really uneconomic to install. It's not worth the effort, it's not worth the transport. Then you can easily see out from the EIS feedback that this device is maybe not behaving correctly at specific extreme conditions. You can do that in real operation conditions with high power, and also multi-channel, you can really speed that up when you have a whole batch of that. If we sum up everything, we have here 10 different steps where typically the workflows are there. I'm sure IEP has that prepared already, but with EIS and with the Gantner combination of time series data, we are in a position that we can get information for all the steps, so you then can do a very quick classification. Next topic and last topic, a few tips and tricks, what we see in the field on applying EIS into the industry. When you start with EIS, you can study papers for hours and read from Chinese scientists what they did and what they measured, right? So your whole holiday can be spent for that. But it's often very important that you start with the right question. What do I want to solve? What is the problem? And if the better you can narrow that down, the more focused you can do that. Well, that's not something specifically for EIS. That's always in the research thing, but it really helps a lot that we are not just doing theory at the beginning. We can measure, see the behavior, does it make sense, and then optimize. So it's a very iterative process. And on the second thing, when you want to focus on the quality control tasks, you don't have to measure the full EIS spectrum with 100 frequency, wait for 30 minutes and so on. You can just say, okay, these are my 4 points, quickly create a list, go to that key characteristics and have already a pre-qualification of the device under test. So you can speed that up. That's, by the way, also possible with our system. And as always, a lot of topics can be solved very quickly if you really simplify the things and separate it. When you understand how a battery is built up, when you understand the history, you can really get your process under control when you focus on that key parameters, on that boundary conditions, and not just try to solve 99% in the first run. And the last one, statistics. EIS is helpful for the change as a relative measurement method. It's not absolute. If you have no EIS measurement at beginning of life, it's hard that you can say what is the degradation. But when it comes in, when you stress test it, there is some change. And this delta helps you. And I think when you have statistics about extreme testing, how often you cycle it, how the Nyquist plot changes, that helps you to give you to do some day-to-day comparison and so on. With the Gantner thing, you have one-stop shop of all the things what you can measure, and I think that's quite helpful that it can be used for your target applications. It is a true multi-channel system, so there is no multiplexing and so on. That really allows you to make everything faster and everything time synchronized, so you can trust the data. And you can also combine that with temperature, strain, and video, whatever. So that's our idea. Once again, the customers. But in Portugal, you know, that's the slide I added because you're really starting in a phase of massive battery deployment. And for that, you need testing and qualification and calibration and very good diagnostics, especially when you want to enter into the battery and second life battery world. And I think that's quite important that these methods and guidelines are set up at the beginning when you start the growth, because at the end, it will turn out, and I'm quite sure that we will have that without eyes, you're just another person with an opinion. And with that, I want to thank you for your attention. I think with systems and discussions and measurement setups, we can put that data into information. And at the end, with that information, we can help our customers. Thank you very much.
Okay, Jörg, thank you very much. I would like to give the opportunity to our online participants to ask a question. So if there is anybody online, you can open your microphone and just quickly introduce yourself, your name and your company, and ask Jörg a question.
Right, we have a question. One moment, please.
You have one question, Modesto?
I have also a question, yes. Hello, Jürgen, and thank you very much for your presentation. We were talking. I'd like to see you just talking a little bit more about the use of EIS for predictive maintenance. Even someone from the audience was asking something similar to that. Is the correlation between the impedance measurements for predicting, for instance, like an incident like the thermal runaway of a battery or a cell? Thank you.
Yes, there is a correlation, and there are a lot of papers written about that you can find with EIS, the thermal runaway indication, earlier than with other measurement methods. So that's the case. We at Gantner are not doing that thermal runaway test, right? We equip the lab like QL, like TÜV with the capabilities, and from there we already saw data and get the feedback that it quite works well. Okay.
Okay.
Someone wants to... Sorry. Is there someone else who... Oh, okay.
Yeah, yes. Neza, we can request for you, please.
Yeah, so my question was, hi everyone. So my name is Neja. I'm coming from Pyralis Advisory. And yeah, I had a question which already before a colleague has asked. So my question was, how can we see the thermal runaway or any type of this risk, how much in advance we can see it before the thermal runaway really happened with EIS? What should we be careful on? And is this something that can be also implemented already in the systems or just on the laboratory scale?
For the complete answer, you need a better expert on that, because on their chemistry, they know everything. And the question is a very good one, but it is a very sensitive one. Nobody wants to disclose all the details on his chemistry on that, right? So we can, the limit, what I see in the literature, it's not, the time constant and all that stuff is not disclosed. So in all the details, what you need, or what you would expect, but when you're doing the tests, then you can get your know-how, your model out of that quite quickly. This is what we know. We are not the ones, again, who are doing the thermal runaway testing. We just provide the data that you can really correlate the things. So I cannot fully answer everything to your needs, I'm sorry.
Not an issue. Thank you very much for your answer.
It's me. First of all, thank you very much for this presentation. I'm Hazal Gergeroğlu from INL. My question is regarding to the temperature measurement. I assume that you have thermocouples in your EIS instrument to measure temperature, because I saw current and voltage at the same time. You are measuring full parameters during a, I was just...
Yeah, we go for the other cabinet.
Yeah, it's thermal camera or it's thermocouple?
We have, there's one picture of the cabinet, this one, right? Yeah. So we have on the full orange line, these are high voltage DAC modules for you can equip the system with current, voltage, temperature, PT100, thermocouples, strain gauge, data acquisition modules.
So during cycling, during the EIS measurement, you can simultaneously measure temperature. So, okay.
Thank you for pointing that out. That's really, I think, when you want to do very detailed analysis, you have to combine the EIS information with the time series information. If it's synchronized, it is a lot of help. If you do one after the other, you have different conditions, so it's help, not a lot of help.
And one quick question more, I'm sorry. These thermocouples outside of the coin cell, right? It's like X2.
Wherever you want to place it, wherever you can position it. So if you have second life batteries, we cannot open that and put the temperature sensor in it, right? So people place them, for example, they prepare the module that they place it between the cells, or they glue it somewhere outside. Some battery labs prepare the thermocouple already as part of the coil, so you can measure it directly where the temperature is. So these are different options. We are the one who can measure that sensors and include it in real time into the data streams.
Okay, thank you.
Mm-hmm. Any other question, comment?
Hello, thank you for your lovely talk. I'm João Cardoso, also from INL. So my question is, when we're doing this analysis, we have we may have our overall state of health of the module, but most of the cells inside may be healthy, but maybe one or two, or an area where the state of health is lower, or it's. Is there any way using any of these systems that we can sort of deconvolute to know that the overall state of health of the module is at a certain level, but there are some cells that are healthier and some cells that are not so healthy and may lead to problems in the future?
I think so. The IEP system, what we will have on the demo later on, is measuring each cell plus also the full cell stack or the module. So when you have 16 cells and you add the 16 Nyquist plots together in the right way, you should end up with the full stack Nyquist plot, right? If that doesn't matches, then you have some outlier, and you will see that easily. The data, what we will see on our live measurement on the demo there, how the different cells are changing. And then you do that experiment at one temperature, maybe at lower temperature and higher temperature, and the different state of charge, and then you will see if cells are outliers or not. And that's why I also mentioned on the point with the statistics, it's quite important that you do tests at different operation conditions to identify the extremes. And the more you have understanding about your type of cells, then you can reduce the frequency of the different testing points.
Thank you.
Okay. Any other comments? Here.
Good afternoon, everyone. My name is Peter Andrade. I'm a PhD student at CES, Electromechatronic System Research Center. And I have a question. In that figure, you have there your bidirectional power source, which is what causes the perturbation in the system. It itself already has some impedance. How do you cope with that?
We measure at the device under test. So we measure with a very high impedance, of course, the voltage at the device under test. The setup, like the cabling and so on, that has an impedance. So you have to make sure that you are controlling the current and the voltage which is applied to the impedance. And I assume you are referring to the point that with high frequency, that cabling setup may change your amplitude of current and voltage. Is that the direction you're pointing to?
No, I'm saying because you are using a programmable electrical load, right? And it's basically a variable resistance. And it itself, because it has some electronics in it, has an impedance already.
Yes.
So when you are disturbing the system with a certain frequency and you are measuring the output of the battery, the current and the voltage, itself will have a part that its impedance is caused by the electrical programmable load.
So,
and how does IES can decouple these two effects?
Two-part answer. The first one is we selected the right power source that we don't have the problems. And the second part is the power source itself discloses where it has the impedance. And when you really go in all the details, for higher frequency, the amplitude is reducing. But this is always depending on the device and the test plus the setup, okay? So when you do high current setups, it makes sense how you do the wiring, how you route the copper bars. I mean, we talk about 305 to 4,000 amps and so on. That makes sense. You have that in every setup, so that's not a specific topic for Gantner or for any other vendor. You have that, there you have to understand where you are and how you overcome that. You have different options. You could increase the amplitude at that frequencies to go in to make sure that when you want to modulate with 1 amp and only 0.7 amps are reached in the device under test at 5 kilohertz, for example, then you can increase the amplitude at the power source to make sure you have 1 amp at the device under test. So that's the thing. You can do that for your setup when you know exactly what is your impedance of the surroundings, but that may change with the next battery type. So it's always an individual thing. When you are on that level to optimize things, then you already have a very good standardized approach how you set the things up, and then you can really simplify a little bit the effort to optimize these things. To help the customer with that, we are also storing the applied current, which is at the device under test versus the one you put there in the output. So you can always see that threshold. And one thing, what you also want to stress is that the raw data from each measurement is also available and stored. So you don't have to trust the impedance, what Gantner machines are telling you. You can also calculate it on your own, because you have to understand what's going on, which helps you that when you want to test all the things, you can immediately find out where you are and how the different setups are behaving in terms of cabling and so on.
Thank you.
For the sense, we suggest twisted pair cabling, shielded ones, and yeah, don't go with too thin cables when you have a lot of hundreds of amps, right? Okay. Any other comment or question?
Okay. Well, thanks very much, Jürgen. I think we will close the online session now. Thanks everybody online for attending. We will distribute a copy of the presentation to all attendees. So watch your email inbox. Thank you very much.
Thank
And
you.
then for the people that want to join us to the new lab, as I mentioned already, it's a short 5-minute drive. I think we'll take a short break now here. This is a very advanced lab that has a lot of new equipment. It's still in the building process. The only one thing that it doesn't have is an address. So
Number. It's a street name. There's no street number.
So, but Modesto will explain you how to get there. You want to explain or give an address? Or
I can just try.